Uh, our project is predicting salary based on name. So the goal of this project is to take input your name and output a predicted salary. So most groups, they try to find correlations between name and jobs. We took a different approach. We tried to find a correlation between your name and your ethnicity, and from your ethnicity, a predicted salary. So the way we do this is last names typically have the same structure by nationality. So Croatian last names usually end with ich, as you can see in our examples. Kovacic, Babic, Maric, Juric, all Croatian last names have that same IC structure at the end of the last names, and we're going to try to make a network memorize these similar traits. Not only for Croatian nationalities, but for Korean, Chinese, Icelandic, Polish last names, they all have similar structures. So for Icelandic last names, they usually end with son, Helgason, Sturluson, Grimson, and Polish last names usually end with ski, like for instance Kowalski, Kowaleski, Nowakowski, Nowicki. So we're gonna train a RNN and see if we can improve on that RNN to predict ethnicity based on your last name. So our data set consists of 19 nationalities. Each nationality contains more than 50 last names. So we're dealing with around 1,000 last names for each nationality. Or not each nationality, in total. My bad. So in order to process textual data, we need to one-hot encode every possible character. So this is because we need to input tensors into the network. So for every last name, we get each character and translate that into a vector that's represented as a 1D sequence of zeros and ones, where the one represents the location of that character. And so an example of a last name as a tensor would contain the first element as the sequence length, the second element as the batch size, and the third element as the number of different characters in the one-hot encoded vector. So if I were to predict my last name Kwan, that would have a sequence length of 4, batch size of 1, and the total number of different characters is always going to be 57. So our RNN structure consists of a simple RNN that's, when you unroll it through time, its hidden state is always passed on to the next RNN. And at every time step, that's connected to a softmax that outputs the probability of each character belonging to a nationality. So at each time step, we're predicting whether the character belongs to a Scottish person or a French person or person of Chinese descent, and we only care about the last time step, which outputs the final predicted ethnicity. So we use a standard cross-entropy loss, which utilizes the softmax function, and we're taking the negative log of that. So basically, we're incentivizing predictions that are 0, meaning that they are wrong classifications, and we want to promote the predictions that have a 1, meaning that belongs to the true class. So for our performance on a single layer RNN, we trained over 100,000 iterations, and we achieved a validation loss of 1.54 and validation accuracy of 76.64%. Our confusion matrix shows that the most commonly incorrect predicted last name is Greek, for reasons maybe being that the sequence lengths were too short. Another commonly misrepresented last name was Vietnamese. So now that we have a network that predicts your ethnicity based on your name, we map your ethnicity to an average salary. So based on Wikipedia data from 2016, the highest ethnicity, the highest earning ethnicity was Indian Americans, making $122,000 on average. Second being Taiwanese Americans, making $90,000 on average, and so on and so forth. So basically, we're predicting a ethnicity and mapping that ethnicity to a predicted salary. So, as I stated earlier, we're using a very simple RNN network, but there's a lot of drawbacks of that, mainly being that an RNN suffers from the vanishing gradient problem. So we use an LSTM network to help fight that problem, because LSTMs involve the use of a carry track, which holds the long-term state of whatever sequence it's trying to learn. And another improvement on our RNN with the use of LSTM is adding more layers, and we also use batching, which is a hyperparameter of an LSTM. So batching saves more time and also allows the network to achieve higher accuracy based on whatever batching size you use. So as I stated earlier, an LSTM cell it's basically an RNN with a carry track, and the carry track holds the long-term state of the network, and the different output gates, the forget gate, input gate, carry gate, output gate, those are all networks that help each cell learn the structure of last names. So this is a visual representation of how batching is a hyperparameter. So using a batch size of 4, we input 4 last names at the same time step. Previously, we were using a batch size of 1. So now we are training the network at the same time with more data. So it's going to train quicker, and it's going to learn more representations at the same time. So in order to do this, we, as before, change each name to a one-hot encoded vector. So these numbers should be, this is just a visual example, but in reality they are of size 57, where that number represents the location of where there's a 1 and the rest of the vectors are 0. So if the batch size of last names aren't the same size, then we need to pad the vectors, meaning we just put zeros for every empty space. And then we reshape these last names. Once the last names are reshaped, the batching process translates each individual, the first character of each sequence. So for the A, S, H, and S in Adloff, Sloan, Harb, and San, those are processed at the same time. Then the second character of each last name is processed, and then the third character of each last name is processed, so on and so forth until the very last name, the very last character is processed. If one of the sequences do not have a character because the last name is short, then all we have to do is just similar to padding, where we just input a 0. So as you can see, the 0, the null representation of these embedded vectors all contain the same values. This is a visual representation of batching. So we've reshaped our output so that we have a hidden unit for each name, and then we do max pooling. So for each hidden unit, we take the maximum activation for each character. So for the first hidden unit, for the name Adloff, the maximum activation was the character V, so we're taking that activation. And we do that for every example in our batch. So each last name has a hidden activation that is max pooled, so we're only taking the maximum output. And then these maximum outputs are then translated to a softmax activation, where this is the final step, and we basically predicting what's the highest probability of the last name belonging to a certain ethnicity. So once we have that, our network achieves, we trained this on 20 epochs using a 2-layer LSTM network with a batch size of 4. We achieve a train loss of 0.62 and training accuracy of 0.8. And more importantly, we trained our validation loss to a score of 0.59 and accuracy of 81.54%. And this is our confusion matrix where each entry is a number representing the number of right classifications. And so each column represents a nationality and each row represents a nationality. So we should see that every diagonal element has the most number of correct classifications. So these are our results. Inputting professor's name, we predict that he's Chinese and he makes around 90K. We predict that one of our teammates, Jigar, is Chinese when he is not, but he makes 90,000. Yeah, so our network has a accuracy of about 80%. It's not completely foolproof. One remedy for this would be to increase the data size of our training set. Some classes such as Greek had around 50 last names, so obviously there's more than 50 Greek last names. So if we increase that data set size, we give more representations for our LSTM network to learn. And that is our project.